So this is where we left off yesterday, right? I'll do a quick review. Hold on. We have identified what vectors and scalars are back review that we did before. Then we were able to go ahead and play around with start identifying vectors from their actual magnitude and direction, right? And we started using the clockwise, counterclockwise method where we start using the angle to really define direction. I also talked about how we were able to start using coordinates as north, south, east, west, right? So it was being able to kind of say where things were, right? Then we started doing some vector equations to where we're seeing how vectors were added up together to how to do that, addition of vectors. And then we talked a little bit about components, right? So each vector component has a vertical and a vertical component and a horizontal components in 2 dimensions. The vertical goes to the Y, the horizontal goes to the X. And then that even gets us to even talking about now the quadrants that we know, like in DC, like north, south, east, west. And so we talked about that. And then we related to now when we start relating these vectors, how can we start finding these different components? And that has to use trigonometry. So we have SOHCAHTOA, which we have sine, cosine, tangent. And then using that same thing to find the individual components, right? Then we had to add the last part of math, Pythagorean theorem. Then once having the Pythagorean theorem, we're able to find the different sides as we go through. So yeah, we're able to play around with that. And then Pythagorean theorem brought us to understanding the different special triangles, right?
Can I just stop you? To the one before.
Say it one more time.
Like you see this one right here, these equations, these ones right here. You see where the 240 is? Hello?
Say it one more time.
Do you see where the 240 is? The 240 degrees on the last triangle?
Yes.
Okay, so everything was easy except for, like, I understand everything except for the slides before this one with those triangles. Like, I understand the R, I can't think of the word. It's not receptor. Yeah, this one, that one, these ones, the R word, the remainder, that one.
The resultant.
The resultant. So the resultant part is the part that I had a hard time trying to grasp the concept. This is where it got confusing, was just these problems, these two. I understood everything else. I'm sorry, what?
What's the confusing part from these? Because this is the same as this one. These are the same as this. Did you understand these?
Yeah, I understood the A plus the B plus the C.
This is the same thing.
So just say 7 was, I'm saying, did we split it up in 2 parts? Like these are 2 different problems in one, right?
Yeah, these are 2 different problems, yes.
Okay, so it'll be the 7, the 5, and then the resultant, and then it'll be the 5 and the resultant. That's the part that I have a hard time with. What would the opposite side be? That little triangle?
Hold on, I'm trying to draw with my draw real quick. When we're doing vectors, we go from end to end, right? So we go from here to here because we went from here up here, then we went up, then we went across. But our actual displacement from our start to our finish is from here to here. So that's our resultant vector. So when we pull that out, right? Now we can make a whole triangle off of that, right? Because we know these values. This up part, the vertical part, is 5 because we see it right there. This part right here is 7 plus this 5. 7 plus 5 is 12. So now if I make my triangle again with these new numbers, I have 5, 12. I take the square root of, if I square 12, I get 144. I square 5, I get 25. 144 plus 25, 169. The square root of 169 is 13. Then you get the same thing over here, right? So you go 7, then you go 12, and then you go 5. Now you go back up 7. So really, you end up here. So how does that triangle look? You have across 7 plus 5. Then you have 12. Because the direction is different, instead of me doing plus 7, I'm going to do minus 7. So now I get 12, 5 again, which we just figured out was when you take the Pythagorean theorem, you get 13. But it all starts from finding your start to your finish, that resultant vector. Does that make sense?
So for the first part, we do 7 plus 5, and that equals 12. This is for the first problem, right? The 7 plus the 5, and then
yes.
Okay, and then because I see the opposite is the 5 too. So then we take the 12 and multiply by 5 and then get the square root of that.
No, I'll skip a step. Hold on. So that's the Pythagorean theorem, right? So that's the thing we covered at the very end, right? So now we just take the two sides, and we got 5 squared plus 12 squared. I'm gonna go up here. 5 squared, 25. 12 squared, 144. When I add those together, I get 169. That's still both equal to this thing C squared, which is the last side that we don't know. This C over here, we don't know this side. So now to find C, we have to take the square root, because if I take the square root of this side, it'll just be C. So then if I take the square root of this side, then I'll get what C is. The square root of 169, 13. Does that make sense?
Yeah. So then my part is what will we do with the other two? Oh, that's why we did the 5 square, because the 2 5s. Now I don't know if I'm confusing myself or what, because it's 2 different triangles.
Are you talking about this problem and this problem, or are you talking about right here? You see a triangle here and you see a triangle here.
Yeah, that I see two. Like, no. What I'm saying is, you see us like crisscross. Isn't that two right triangles? If you drag the resultant from the 7 to the 5 at the top, that's two triangles.
Yeah. So now you got here, right? You do have these two triangles, but we're looking at the whole big one. You want to look at the big one. The one that's created by using this part and this part, right?
Oh, okay.
That's what we want to look at. Make it easier on ourselves.
Okay, maybe that's where the problem was. Okay.
Are we good with this one now?
Yes, thank you. So then we would just look at the whole big thing for the,
Yeah.
so it'll be 7 squared plus whatever 12 plus 5 is.
Which one are you talking about?
The next one, the one beside it.
Now do this one. You go
Okay.
7, then you go down 12, then we go across 5, then we go up 7. So we really start here. And then we go across here. So what is that triangle? It's really this. So let me pull that out. I got 7 and then this 5 right here, right? So I'm gonna add those together. This is 12 minus this 7 over here because of the opposite directions. So now you have those, and then you just take those together. And let's make a whole new triangle. 12 and 5. Which we established is give us that 13 over here. Does that make sense?
It's the same triangle? Okay.
Once you see the numbers, and that was a special part of why let me transition into. We talked about these, but I really talked about these to get into talking about the special triangles, right? Common right triangles. You got the 45, 45, 90 triangle, and you got the 30, 60, 90 triangle. Then you have a 3, 4, 5, and then a 5, 12, 13. The last two really are related to Pythagorean theorem, right? So where you have two sides that you know, and you could be able to figure out the fifth side, the third side. And just by knowing these ones, you don't have to do any math to confirm it. You could just go ahead and use it. And like in this practice problems, we'll see more common ones like these, the 3, 4, 5, and the 5, 12, 13. You'll also see the ones related to the trigonometric functions, which show the 45, 90, and the 30, 60, 90, right? To where you'll have the 45 because they have two angles the same, right? So that means the sides are the same. So then the hypotenuse is going to just be that side times root 2. Same thing over for the 30, 60, 90, right? The smaller angle, which is 30, will be across from the smaller side, which would be x. Then across from the 60, we have x times root 3. And then the hypotenuse will just be double the small side, which would be 2x. So if you can remember these, you don't have to do math. So let's try and use these to help us out when it comes to these next problems.
Wait, could you go back one time? I'm sorry. You said it so fast, like I'm trying to write while you're talking, but now I'm gonna stop writing so I can listen. So could you say that one more time, please?
Which part?
You was just the only part I really registered was the we don't have to use I don't really remember.
This is like, yo, you can kind of remember like that these values come with these triangles, right? So if you see a 45, 45, you can remember that the two sides are going to be the same. And then when you see the 3, 4, 5, you can know if I know I got two sides that's 3 and 4, that one of the sides is going to be 5. The last side is going to be 5. Then if I have the 5, 12, 13, I know that the longest side is going to be 13.
Or do they have to be these exact same numbers is what you're saying?
Yes, they have to be the same numbers.
Oh, okay. Thank you.
Yes. Does that have it clear?
Yes, thank you so much. I didn't understand that.
All right, so let's keep going to this next problem. All right, give me one second. Hold on. Okay, now we have this one, which is basically the same, but now we just want to find the vector components and add them together. So now we're looking at this, right? We want to sketch the results and play around what we knew and put this all together to be able to find the result of magnitude and direction by finding its components, right? So let's look at this first one. How does that big triangle end up looking from start to finish? We know. Go ahead.
I was gonna say the 5.
Mm-hmm. What about the 5? From where to?
It goes up, right?
Up to where? Where do we finish at? At the end of all those vectors adding together.
I say the 5 to the 4.
So let me draw a line. It's a bad line, but I got to figure out all the mini components in between there to get me from there to there, right? And what is that? That's here, here, and here, right? And what we see is in this one that's diagonal, right? So these are obviously just 5 and 4. So those are just across. But what is this component right here? How do we find that component?
Could you say that again?
Do we use the 30 degrees, the cos of the 30?
That was what I was about to say. Yes. How do we find that component? And Lakshmi just came and said it, right? Yeah. So we use 30 degrees, right? So what we could do is this, right? We could go here, right? Take this triangle out. Sorry, I'm doing really bad. Here, right? And then we could say we want to find this one, or this could be Y, or this could be opposite, and this could be adjacent, right? If I want to find this one opposite, I could do sine of 30 equals opposite over what, 12, right? So then I just multiply 12 by sine of 30. I do the same thing and do cosine of 30 for adjacent. And give me adjacent over 12. So now just multiply 12 by each one of these, right? But let's make this easy on ourselves, right? What did I just say we could do, right? What's the angles in that triangle? First, we see we have 30 degrees, right? Let's assume that it's a right triangle. So then we have a 90. What's this next angle going to be?
60?
What did we say about 30, 60, 90 triangles?
They just I just see an X, 3X.
Yep. Okay. So where does the X go? Across from what angle?
It goes at the long part, the hypotenuse, right?
That's which one? X or 2X? Did you write it down?
2X is the hypotenuse.
Good. 2X is the hypotenuse. So the X is across what angle?
The adjacent. I meant the opposite. Sorry, the opposite.
So let's start from the 30, right? I'm going to put it here because this is a smaller one. So then if the X goes here, which one goes here? You said it earlier.
The 3X, the X,
Close.
3X.
X root 3. So now let's apply that to the triangle that we have so far. We know that this is 12 and this is 30, right? So we know this 12 is pretty much equal to like our 2X over here, right? So if 12 is equal to 2X, what would X be equal to?
6.
6. So we can put 6 over here, right? And then we know that this one is X times root 3. So now we know over here we have what?
Wait, so if we have could you say it again?
X, 2X is over here on the hypotenuse, right? We know that the
Okay.
actual hypotenuse is actually 12. So
Okay.
now because we know that, we could find out what X is, right? We just divide by 2. So if we divide 12 by 2, we get what?
3.
12 divided by 2.
Oh, 12 divided by 2. Sorry. It's 6.
6, right? Good. So now we got X. That's over here, right? Now over here on this one, it's X times root 3. We just found out that X is 6. So on this line right here, it should be what?
3.
Root 3, but times what?
3.
Times 6.
It's times 6.
So I'm gonna write that here. Now this is the actual number that we can actually find. Now we are able to find the components and we can add them together. So now we could take this and bring it over here.
Seriously, I can't. I don't need to be on the phone. I need to leave that phone right where it's at and concentrate.
When we make our new triangle, it goes from here to here, right? we can now add all the pieces together, right? So now on the bottom, what do we have? We have 5. Hold on.
So 3 times 6.
Root 3 times 6. We got 5 plus 6 root 3 plus 4 on the bottom, right? And in the top part, we have 6 because we added by the components. So that's our triangle, right? So now we have that. So we just got to add all these together. Now, root 3 times 6 is an actual number. Let me find out that number is.
It's 10.4.
10.4, okay. 10.4 plus 5 plus 4. So now we at 19.4. So now we make this new triangle here. We got 19.4. And 6, right? So to find this side, all we're going to use is Pythagorean theorem. So let me just start erasing. Then we put all those together, right? I know 6 squared is 36. So you got 36 plus, got to figure out what 19.4 is squared. $37, 360, 376, 376, 36.36. And that's equal to C squared. So then you just add those two together and take the square root. So it's like 412. And then you take the square root of that. We get about 20. 20.3. If anyone did it themselves, did they get the same thing?
Yes.
All right, cool. 20.3. That's the math part, right? So now that we know how long that actual vector is, right? Now we need to figure out the actual, direction that it's at. So now we're just trying to find a direction. Now we just need to redraw that triangle, and let's use our trigonometric functions real quick.
By direction, do they just mean the angle?
Exactly.
Okay.
One more time. This is what, 19.4, 6, 20.3. Now we just need to find this angle. To be honest with you, I'm just going to use the easiest one. I'm going to just do tangent of the angle is equal to the opposite 6 over 19.4. I'm trying my hardest with this trackpad to make it clear. What you're going to do, though, is take the inverse tangent. Inverse tangent of both sides. This will end up just being theta the angle, but then you want to come over here and take the inverse tangent of 6 over 19.4. So on my calculator, I'm going to put in 6 divided by 19.4. I got 0.3, and I'm going to go press the second button and then press inverse tangent. So it gets the inverse tangent, -1 of 0.3. And I got 17.1 degrees. Now, what does that mean? That means that if I rewrite all of this, right? My vector should look something like this. 20.3 at 17.1 degrees. Now, in hindsight, 17.1 degrees, what quadrant is that in? What direction? What quadrant is that in first? First, second, third, or fourth?
The first.
First. So then when we look at the quadrants, remember, we got first, second,
Northwest. I mean, sorry, that's northeast. Northeast. I always do that.
northeast, right? So that's northeast. Does that look like it's going towards northeast?
To me,
Sorry, from this right here, from over here. Does this look like it's going northeast?
no.
Over here.
Look like it's going to the east.
This right here.
Oh, which one? The one at the bottom?
No, right here.
Oh, okay. Yeah.
Good. So that 17 degrees will put us over here, right? Something like this. What we're trying to just check is make sure that the number makes sense with what we see in the actual diagram. And 17 degrees going towards northeast looks like the diagram. So that makes sense. So I think we did it right.
So when we're finding the angle, is it always the angle between the hypotenuse or like the vector and the x-axis?
You want to say yes, because it's the angle between like, yes, like where it connects at. So I would make generally use the x-axis.
Okay, thank you.
All right. That was a lot. Well, let's try and do the next one, right? Let's see if we can walk through this one. All right. So we're going to have to do the same type of thing, right?
We can't see your screen.
No, I reshared, I know. All right. So we got to do the same type of thing, right? Now, we have to find the components, right? Let me not say it like that. I want to find from this vector to where do I end up at? Here, right? Oh my gosh, that was awful. From here to here, right?
No,
Why you say no?
I guess I was looking at it wrong. I was going to say at the top of the triangle, but you're right. It would be at the bottom.
Because where did I finish at? Let me follow the path. The arrows actually tell me where to go. Boom, boom, boom. Displacement,
Very much so.
here to here. We need to find that. But to find that, we need to figure out what's this length here and what's this length here to complete it. Inside of that, we see we have a triangle, right? Let's pull out that triangle. Now you tell me this angle is 45. And we're assuming this is a right triangle. What's this other angle?
I don't know.
Take
45.
2 seconds to think.
45 and 45 and 90.
Because that adds up to what?
I don't know. X.
You- Hold on, think. 45 plus 45 is what?
$90,
90 plus 90 is what?
$180,
How many what's the total amount of angles in the triangle?
$3,
It's 3 angles, yes, but they all add up to how much?
$180.
180. So that's how you know you can figure out the other side will be 45. Other angle will be 45. Now we established this earlier, right? If two angles are the same in a triangle, that means what about their sides?
It's subtracted by them or something.
Think about it. If the angles in a triangle are the same, what do you think the sides are going to be?
Oh,
The
they're
same.
equal length.
Equal length, the same, congruent. Good. So now I know that this side and this side is going to be the same. So all I have to do is find one of them, right? Now I can use trig because they gave me this 14, right? But what do we know about 45 triangles? Write
Nothing.
it down. We know that this one's going to be X. This was going to be X. This is obviously 45. This is 45. Do we remember what this one is?
14.
It's 14 in this, but do we remember what the from the
X2.
close? X root
X
2.
square root 2.
There we go. Good. So now I know that this is 14, right? Which is X times root 2. So if I want to find out what X is to get these two sides, I have to divide 14 by what?
X2. X square root 2.
Just root 2.
Just root 2. So I just take this root 2 and I divide 14 by it. So really you just do 14 divided by root 2. Now, that's not the proper mathematical way. I'm not going to lie to you, but I'm not going to spend too much time on that. So on your calculator, just do root 2. So, sorry, just do 14 and then divide it by root 2.
It's approximately 10.
Approximately 10, 9.8, right? 9.89 or 9.9. So you got X is equal to about 9.9. So now we know that this top one is 9.9. And then now this bottom one is 9.9. I'm writing on the completely wrong one. I apologize. This is 9.9. And then this is 9.9. So now what do we do with that information, right? We add all the components together. So now let's make our new triangle from here to here. We're going boom. So where we go across and down, right? So we got down. We got 9.9, because that's how far this one is, right? Minus 5. And I really could do it the other way so it'd be negative, but I'll just leave it to where it's here. Actually, no, I'll do it that way because that'll make sense. Hold on. So we started going up 5, so I'll do it that way. So then we get to negative 5 minus 9.9 because we went the opposite way. Then we got that top one 9.
Yeah, I think the top will be 9 plus 9.9.
9 and then plus 9.9. Okay, cool. So then when I rewrite it, it should be 18.9. And then negative 4.9. I'm keeping the negative on purpose, right? So now, once I get here, right, now I'm able to do, what is it called? Pythagorean theorem, right? A squared B squared equals C squared. $18.9 squared plus negative 4.9 squared. If you kind of estimate that 4.9 is about 5, so it should be around 25.
I'm hungry.
This is sloppy. It's 357.21 plus 39 was sorry. I'll just do the total so I don't so crazy. When you add them together and square them, you get about 381.22. Then you're gonna take the square root of that. Please do not stress too much about this math. So where you get about 19.5. All right. Now we got 19.5. So let me erase all of this. New triangle, right? From what we just got. Minus 4.9. $18. .9, and then we got 19.5. So now we're doing this, right? I'm gonna just do the same thing. I'm gonna do tangent. So find the angle. I kept it negative for a reason. I'm just skipping ahead, to be honest with you. But you still want to do tangent of the whole thing, right? Over the ratio of opposite, what angle we're looking at here? Opposite 4.9 over 18.9. So then for an angle, most likely going to get something negative. Yes. So now I got negative 14.5. Now, why did I keep the negative, right? Think about it in regards to our unit circle, right? We said this was 0, this was 90, this was 180, this was 270. And when we go counterclockwise, we go this way, right? So if counterclockwise is this way, right? And all these angles were positive, right? Clockwise will be what? If we go, go ahead.
Clockwise will be going to 270.
Which would be positive or
Negative.
negative, right? So if I just got an angle that said negative 14.5, right? Is that what I just got? Negative 14.5. Which way would I go? Positive up this way or negative this way? Or should I say towards the 90 or towards the 270?
Between the zero, like in the bottom, like bottom right.
So that's where it comes in of from the x-axis. I'm going to measure 14 degrees from the x-axis going this way. This would be negative. So where now this angle right here is negative 14.5. I didn't put the negative sign, just try to squeeze it in there, right? But I basically just started from here and went the opposite way and got 14.5 here. Because if I would have went positive, it would be 14.5 here. But I put negative. Now, does this direction match up with what we have over here, going from here to here?
Yeah.
Okay, so now this shows us now we have two ways of representing it. You can represent it as negative 14.5, or let me change the color. If I start from 0 and go all the way around, now what angle is this?
Uh, 180.
Don't guess. Take a second. Go
Wait,
from 0 all the way around.
Oh,
we're
that's a
still back
circle.
to 270.
You close. You getting there.
360 minus 14.5.
Exactly. So now we have that full angle, right? So that's how you can represent it from the positive. So that would be 345. So it's different ways. Why I'm saying it that way is you can say it 345.5. So now
So if
when
we
we
get a
compare this,
problem that's like in the negative side of the quadrant, we should do the step.
it's just when you do your math. So like you see how I could have very much just made it positive and just treated it as negative, right? Like treated it as a direction, right? But I actually, when I did my math, because you see how we started with 5, we went up 5 first, then we went down 9. If you really do it based off of start finish, it's 5 minus 9, right? So now you literally have 5 minus 9 to where you get a negative number. So you're in the south. So like if you literally understand it from there, then you'll see, okay, I do have a direction of negative. So I was just trying to make sure you know what does that mean when you have a negative and how you treat it. Does
Gotcha.
that make sense?
Yeah.
So now when I rewrite it, right, I could write it as, here's my vector, right? What was the amount? It was 19.5, right? Yeah, it was 19.5. At either positive 345.5 degrees or negative 14.5 degrees. Or what quadrant was this in?
Southeast.
Southeast. Make sense? Yes, I am frying your brains with this math part, right? But do we have any questions about how we were able to do vector addition, find components, add them together, and find a resultant?
I'm not gonna lie, it's real challenging because it's like so many components and parts that I don't think I'm gonna just get it in like tonight. I think I just have to go to tutoring and practice.
That's why I'm going through with you now. So that when you go do the practice problems, you can go ahead and at least have an idea to play around with, because I'm only doing one problem. There's multiple problems where you read it the same thing. That's why when you do the practice problems, I'm giving you an insight of it so that when you go do the problem 3, 4 more times, you'll be like, oh, okay, it makes sense. But at least you got to see me do it here in class. So that's what this is for. So now let me take that and let's go to the next problem, because we're not doing this to do math. This is not a math class. This is physics, right? So all this math, all this vector stuff has to come to a head, right? And I'm glad for like the last 30 minutes, right? We're going to start doing some application problems, right? So think about it, right? Say you in a plane, right? And you're flying. When you get in a plane, sometimes and they tell you oh, the weather report. They might tell you, oh, we have gusts of winds coming to the north. We have gusts of winds coming to the south. We have this in the direction of it, right? Now that direction of the wind matters in relative to which way you're going, right? So let's think about these different situations and see how it affects the resulting velocity, right? The magnitude and the direction, right? So say we're going each time with the plane, we're going 100 miles per hour, but the wind has either a different velocity each time, and the velocity could have a different magnitude or it could have a different direction. For these scenarios, it's going to have the same magnitude, but we're going to have different direction. We're going to see how that plays out, right? So in the first scenario, we call this as a tailwind, right? Imagine the velocity, our velocity of the plane is still 100 miles per hour, right? But then we have a wind that's a tailwind. So the wind is actually in the same direction of the plane. So it's coming from behind the plane to go through the plane in the same direction it's going, right? So because of that, and what we know about vectors, right? What would be the total magnitude of the velocity now with this added 25 tailwind?
125.
How did you get 125?
You add them since they're both in the same direction.
Good. I'm glad you added them because they're both in the same direction. Now, would it be in 125, right? What would be the direction? Not a trick question, just look from the arrows.
To the right?
To the right or
East.
east, right? We're going to just say east because they're both going that way, right? Now let's do the same thing, but look at the headwind scenario, right? We added 125 for tailwind, right? So I'll do 100 and then 25. You added them. So for this next one, which is tailwind, right? A headwind, right? So now the wind is coming towards the head of the plane, right? So instead of being in the same direction from behind it to the front, it's actually going from the front to the end of the plane, right? So you're going one direction, the wind is coming straight head on to you. So now look at the direction of the plane and the wind with the vectors, right? Are they going in the same direction or opposite?
Opposite.
So with it being opposite, what do you expect the magnitude to be?
$75.
75. Good. And how did you get 75?
Subtract 25 from 100 since they're opposite direction.
So we still are adding them together, right? But because one is the opposite direction, we have this negative now.
Oh, yeah,
Now
negative.
it turns into subtraction. No, I'm not correcting you. I'm just saying it just in a way you were still
No,
right.
that makes sense.
Yeah. So now, but to catch that really thing, we're always adding, but to really catch that, what makes it to where we do subtraction is the direction changes. That direction changes because we have a different direction. Now we have to add basically a negative, which is a different direction, or we subtract it. So that's why we still have the 100 plus a 25, but it's just now plus negative 25. But in general, right? What is the direction now?
Still to the right, since the 100 is
Use your vocab. You're almost there.
faster than 25.
Faster, or it has a higher.
Like net. No, not net force.
Higher what? M word.
Magnitude.
Magnitude. So the magnitude of the plane is still higher than the magnitude of the wind. So even though we add them together, there is a subtraction, right? The magnitude of the plane is still greater to where the overall velocity is still east towards the east. All right. Let's do this next one, right? We got a side wind, right? So now we're applying to the plane, and on one of the wings, we feel 25 miles per hour going towards the side. Now, with these two, right? We're still going to do the same thing of adding them, right? But how does this really look when you add them together? Let me pull out a picture. Let's say this is the plane's magnitude at 100, right? The side wind is really coming in here like this. right? You see how you see the arrow? And this is 25. Can I just add them together like 125 like I did before, subtract them?
No, you would just complete the triangle.
Exactly. So now I have to complete this triangle.
It's kind of like that other problem that you just did in the same direction.
Exactly. So now, yes, this is exactly the problem I just did in the same direction. So now we have to complete this triangle, right? So now, first, we have two sides and we want to find out the longest side. What will we use?
A squared plus B squared is equal to C squared.
Let's do that real quick. So we got 100 squared plus 25 squared. So what's that? That's 1,000, right? Am I tripping? No, that should be 10,000. Right?
Yeah.
Plus it's 25 squared. That's 625.
Yeah.
All right. So now we need to find out the square root of 10,625.
It's 103.
103. Okay. Now with that, right? Let's go and just be safe. Let's use tangent because we know those two sides and find the angle of it, right? So I do tangent here is equal to, I want to find this angle. So opposite 25 over 100. And like I said before, take the tan inverse of all of that. So then you get an angle of whatever you get out your calculator.
14.
14? Exactly 14?
I don't know if it's exactly.
No, sorry, not exactly 14. Just you said 14. I'm just going for
Yeah.
not exactly 14. But 14, right? Now let's think about it, right? 14 in what direction? Because I didn't put it over here, but what should this 25 really be?
South.
South or negative, right?
Negative. Okay.
So now if you put that negative there, right? What should this 14 be?
Negative 14.
Negative 14. So I got 103 at negative 14. Or how else can I write it? Remember here?
A circle.
All the way around.
360.
360 minus
Negative.
14. What's 360 minus 14?
Like 346.
346. Or what's the directional component that you just said? Northeast, southeast, northwest, southwest, or
East. Oh no, southeast. Sorry.
southeast. Good. All right, let me get rid of all of this. Does that match up what we just did? Does that match what we just did? Forgot.
Yeah.
And the way that they say it, right? They said 14 degrees of southeast. So basically, you could say in the southeast corner quadrant. Hold on. In the southeast quadrant, 14 degrees. So that's what they mean by 14 degrees of southeast, right? Now, how does that apply to a regular physics problem, right? So, anybody ever been in a river, like, or in a body of water where like you're trying to like go across and maybe it's like a down current to where it's like pushing you across, like pushing you down, but you're trying to swim across? Does that make sense to anybody?
The wave pool, does that count?
Yes, exactly. A wave pool. Yes, just like that. So you've been in one before. Maybe you're trying to go across something like that, and it's just like pushing you down, and you got to like go against it, right?
Yeah.
So think about that with this riverboat, right? I'm over where it starts at, right? And I want to get to one of these positions, right? But I have this river that's going at a current of 5 miles per hour. So for me to get to each one of these positions, I have to angle myself or go at a certain speed to make sure that I can get to where I want to go, right? So what we want to do is match each boat heading and boat speed where we would think it would line up at, right? So let's do logically. Let's do the first one together, right? And let's do them in pairs, kind of, right? Actually, let's do this one, and this. Can you see my mouse?
Yeah, I can see it.
Hold on. Let's do this one, and this one together, all because they go in the same direction, right? So I can make it make sense. So now, right? Remember how we just did this one? If I'm heading this way, right? Each one of these directions, I'm heading this way, right? But the river is flowing which way, north or south?
It,
Say it again.
this looks like it's the downward, so south.
South, right? So each time the river's going like this, right? So Lakshmi, you said it earlier, right? The direction is based off of what? I'm going to go to which way?
East.
East, but also.
Oh, like southeast.
So each one of these, I should be going somewhere like this, right? Does that make sense?
Yeah.
So I should be going this way, right? So now for these ones, right? We want to figure out where I'm going to be at, right? Now, each time, this is always going to be 5 meters because the river's going to have the same, right? But for each one of these boat headings, right? The ones was going to the right. What is changing each time?
The speed of the boat.
The speed, right?
Yeah.
So think about it, right? If I was to go, let's say I'm put this right in the middle. Say this is because it's 14, 7, and 20, right? Let's say this is 14, right? I want to redraw this same thing, right? If this is 14, would 20 be bigger, this arrow, or smaller?
Smaller? Wait, I'm sorry. You said 14 was the arrow. It will be bigger.
Bigger, right? So let me make a bigger arrow. That's bigger, right?
Yeah, but it wouldn't be bigger than 21. 20 miles, would it?
This 14. This is 14. This is 14. This is 20. Does that make sense that this arrow on the bottom is bigger?
Yeah.
All right. But this 5 is still going to be 5, though, right?
Yeah, the 5 will stay the same.
Now think about it, right? Now that this 20 is bigger, this top one is bigger, and it's 5, how does this one look now? It should be a little bit
right triangle.
Still right triangle, but do you see how it looks a little bit different? Look at this angle compared to this angle. Does that make sense?
I mean, it makes sense because the numbers make sense.
Now let me try and do the same thing with 7, right? So 7, If this is 14, I'm gonna make this one half of it. Then we got 7. We still got about 5, right? So now we down here, right? Now look at that angle compared to these two, right? So these are the ones that's going across, right? So what can we judge about these angles based off of, the direction of where your destination is going to be based off of these angles and these boat speeds, right? When we have a boat speed of a higher boat speed, our resultant vector should have a bigger angle or a smaller angle.
A bigger. Our resultant would be the biggest, right?
Not the biggest resultant, but I mean the angle size, right? You see how like this one is bigger, right? This is the biggest top one, right? How is this angle? Is this angle bigger than this one?
No. I mean,
Is this
yeah,
angle-
yes. 20 is bigger than 14.
No, the angle. You see this little big angle right here? Is this
Yeah.
angle bigger than this one?
No, they look the same.
Let's say I might have drawn it wrong, but this one's a little bit skinnier than this one. Now this one might be a little bit bigger than this one, right? So as the boat speed goes up, the angle decreases, which means the path that you're going to go is going to be more straight. That's what I'm trying to say. So think about it, right? Which destination do you think you will reach if you were traveling at 20 miles per hour going to the east?
See?
Good.
Hey,
No, you were fine the first time.
okay.
So now, what if you were going 14?
Maybe B.
Think about it, right? Hold on. Let me actually take a step back. We're looking at the ones that's going to the east, right? We already established they have to go which direction? Towards what quadrant?
Oh, south. So it would be like closer to E.
Southeast, right? So that takes out which ones? Can it be A or B if it's going
Yeah, it
towards
takes
southeast?
out those
All right, so now we're looking between which ones?
C through D, C through E, which will make it D or E.
Good. So you just said 20 was C, and then you said D or E for 14. Which one would you say for 14, D or E?
It's D.
Good. And then last one, E would be which one?
The E.
E would be which one?
The 7.
7, right? Okay. Now, let's see if you could just logically, let's just do it real quick. Let's take that same mindset, right? And let's apply it to when the boat is traveling this way. We're still going to go here, right? So now we have our new triangle. So we're traveling here, the boat's here, this is our new triangle. So where we want to see, where are we going to land up at? Now we know it's between A and B, right?
We know it's between A and B. We know it's between A and B because we know everything's going to the east, and the further down we go, it's smaller. It's the south.
So you know what? Let's not even sit here and confuse ourselves. Like, no, you're doing good, but like, let's just take a good guess and just see where it's at, and then we'll look at it. We'll check it real quick. Because you know it's A and B, which one do you think will land you closer? Which one do you think will? Where do you think to 12 and the between the 12 and the 7 you will be at? So these two. Between 12 and the 7. Would you be at A or B?
I guess A.
For which one?
We're on the 14, right? And the 7.
No, there's 7 and the 12.
Oh, the 7 and the 12. The 12 would be B, and the 7 would be A.
All right, let's check. Okay. So we did good. We got C, we got D, and then we got E right here, right? So now for the 7, we got 7 for B and 12 for A. Let me see if I can try and make sure I make sense of it. Hold on. That's how I meant to do it. Okay. I actually haven't done it like this, but let me try and put it all together. Hold on. I was being lazy. I shouldn't have did it like that. But hold on. So now let's think about it, right? When you have the vector like this and this one right here, right? You have to find the individual components. Now, the width of the river is still going to be the same, right? But what changed? How fast I went up. And why I'm saying that is because in this one right here, the difference between this one and let's say this one, let's say this is the 12 and this is the 7, is this vertical part. So when you look at it, right, and I have a down, and I actually know why I messed up. I drew it the wrong way. I have a down current here, right? This has to be added to that to counteract it. But because this is 12, let's say this is like maybe like, I don't know, some number, right? But because this is some number, this one is going to be larger than this one. So therefore, it'll be able to have an overall higher vertical of here versus this one is not as large as that. So it's going to end up being more towards here. So that's why the B ends up being here. This one ends up being B, and this one's going to be here because that 12 has a higher vertical to counter out the river vertical here, so where it's able to go up to the A, versus that 7 doesn't have the higher vertical difference. So where now it's kind of more in the middle to where it gets to like pretty much going to almost being across B.
So does that mean like the faster the boat, the more
Sorry, think about it logically what you're about to say. For you to go upstream against a downward current, do you have to drive your boat faster upstream?
yeah,
Does
yeah.
that make sense?
So if you're going faster, you'll be more like against the current.
Yes.
Okay.
To go against, like if it's going 5 miles per hour down, if I want to go against it, I have to go faster upstream, right?
Faster than 5. And the more faster than 5 you are, the more upstream you will be.
Exactly. Yes.
Okay.
And this is like the same thing with the riverboat, right? So now let's just add the math to it for like the last 5 minutes real quick. So this is the same thing we just did conceptually, but now we're going to do it with an actual problem like math, right? So we want to find a resultant vector of the riverboat, right? So the riverboat heads east on a river that flows north, right? So the riverboat, let me draw it, is going east on a river that flows to the north. The riverboat is at 5.1 and the water is at 3.6. We want to find the direction of the resultant velocity of the riverboat. So here, we got our triangle, same thing. How will we find this third side real quick?
A squared plus B squared equals
A
C
squared
squared.
plus B squared equals C squared. I'm rushing through. I'm not gonna lie. I'm gonna do A squared plus B squared. So 5.1 squared plus 3.6 squared. I got 38.97. Then I'm gonna take the square root of that. So where I got 6.2. A squared plus B squared equals C squared. I use this. Now, to find out the angle, I'm going to take the tangent of both, tangent inverse of the opposite here over the adjacent. 3.6 over 5.1. So then take the tan inverse. (3.6) over 5.1. Tan inverse. I got about 35. So you get 35 at, sorry, 35 degree, what is it? 6.2 at 35 degrees. 6.2 at 35 degrees. Meters per second at 35 degrees. Now, if the river is 70, let me erase that. 70 meters wide, determine the what is it called? The time required for the boat to cross the river. Now, this is where it starts to use kinematic stuff we used before, right? Or just definitional equations, right? We have a velocity. Velocity is equal to what?
Distance over time
Distance, displacement, same difference. You go ahead.
versus
Over.
change over time.
No, you're right. You're right. Over time, right? We know this is 6.2. And they gave us a distance of how much? 71. And we got a time. All we got to do, I'm going to multiply time through. So where I get this now, time times 6.2 equals 71. So now I divide 71 by 6.2. I am moving very fast. But we start off with that equation, velocity equals displacement over time, or speed equals distance over time. So where we get the time is equal to 71 over 6.2, which is
So you use the result, like the resultant
11.45.
vector instead of the actual boat speed.
What did I just do?
Like the 6.2 versus the 5.1. Because technically the boat speed was 5.1, so you would use
Yes, I use the resultant speed.
okay.
And if I'm wrong, I'll come back. I think I should be right. Determine the distance now. I did 11.45. Now the distance that the boat will travel downstream, right? So that entire motion will be 11.45, right? So now we want to find out how long this vector is going to be, right? So if it's going, the boat is traveling at 3.6. No, wait.
Yeah, I think it's 3.6 because that's the direction for 3.
Yeah, so this one moves 3.6, right? But how we have a time, right? So now we have the same thing over distance,
Oh shit.
and we have a time. So now we have 3.6, trying to find the distance over 11.45. Just multiply it through. And it should be like 41. All right, let me just go through and just check all these answers. Yeah, you was right. I messed it up. So instead of using the resultant vector, use actually the across the river stream, right? So pretty much the same thing I just did, but just change the 71 instead of using the 6.2, use the 5.1. So let's do that real quick. And then this will be the last thing. I kind of got a little flustered and was moving too fast. So now let me go back here. When we got that 71, hold on. We got velocity is equal to, let's say, distance over time, right? Instead of using the 6.2, use the 5.1. Then set that equal to the distance 70 here. And then come here, here. So where now you get T equals 71 over 5.1, which then gives you about 14. So now when you get that, all you got to do now is come exchange that 3.6 over the distance that we just did times 14. So then you get 14 times 3.6, which equals about 50. So using the different vectors to be able to predict and figure out the different quantities that go along with it. But that's how what we just use with vectors can be used to actual real world problems, so the riverboat problem, right? All right. That was a lot, but we're almost done. We're still on pace. We got projectile motion and then our final wrap it up question. So be prepared on Monday. I'll probably do class. Yes, Monday will most definitely be in person. So where we can go through, wrap this up, and I'll even kind of transition this into 4. I maybe do a Mentimeter too to kind of bring it home. But we're on pace to finish this one and 4 in enough time before April, so where we can really do the practice problem in person and kind of make sense of all of this. Real quick, hold on. Before y'all leave, once again, I will put it on there later, but I need everybody, if you haven't done it already, fill out this form. Fill out this form. It looks like this. Put your name, first, last name, your UDC email, put UDC, your major, undergraduate, and just put right here that you're interested in using the Black Opal software. We'll start using this as soon as we get access. You can leave this part blank and then press submit. I put it on here. I will put it on Blackboard, but just right now, everybody submit that. All right. Any questions for me before I let you guys go?
I have one.
Wait, is this class related or is it
Mm,
about the work?
It's related to class, but not this class.
All right, hold on. Let me stop the recording.